Okay, good morning. So yesterday we started to talk about fixed beam force. So I want to give you this kind of refreshments and to review that whenever we talk about array processing, so if we have array of multiple sensors, M sensors, and this is a very simple model, so we have something like that, YT equals to, so in the time domain we can also work with convolution, okay, so YMT will be GMT convolved with the desired source plus VMT. So this is the model in the time domain. And we can make some assumptions about the transfer function, the impulse response from the source to each of the sensor. And we have M sensors. In the frequency domain, we have with windows, and then we can give like time frequency beams. So in the slides, I write it in some way, but in the literature, sometimes we write it like this. So each sensor has two indices, time and frequency, like this. And the time, so sometimes instead of time, we call it like R multiplied with capital R. So this will be the index of the time window. But we can also put here time, but this time is different than this time, okay? Because here it's the samples, so with the interval, it's the sampling interval. Here, T is the index of the window. And then we have some jump window. And then we have some jump or this difference, hop, we call it hop between windows. So this is the index of the position of the time window. So here we get like, for each frequency, we get samples. Okay, so even if we fix the frequency, we get samples along the time or the index of the window. And then we can also write it either something like that. So suppose that the transfer function from the source to each of the sensors is constant, so it doesn't depend on time. But sometimes there are movements. The source moves, maybe the array moves. For example, wearable arrays. So if we put the arrays on a person, like glasses, smart glasses, or we put some sensors to measure something on the body, or outside. So many times, either the source moves and we need to track it, and maybe the array moves. So practical situations involve more complicated transfer functions. So that's why we don't work in the frequency domain. We work in the short time Fourier transform domain or other transform are related to window transformed. So short time Fourier transform is very useful because for each window, we can choose the length of the window, and it approximates. Instead of working with joint diagonalization, we work with STFT, which is a good approximation depending on what type of signals you have, okay? And then how do we write it in the STFT domain? So sometimes people write it with a multiplication. So they say, for each time frequency domain, we multiply it with a transfer function like this. GMTF. So the fact that we use for each window a different transfer function, it means that we allow the transfer function to change. And of course, we need to track these changes. But I'm talking about the model. I want you to see that there are different models for working with array processing. Okay? So this, many times, we choose multiplication with the time frequency bin of the source plus V, the noise in the time frequency bin. Okay, and of course you need also models for the noise. Okay, so sometimes it's useful to split just like we talked yesterday or day before yesterday. So we split the noise into at least two components. One component which is correlated with the noise at the reference signal, and the other component is the remaining noise components. And it's also possible to do additional things, okay? But I try to simplify things, the basics. Okay. Here we make a very important assumption, okay? So when we come from the time domain to the time frequency domain, and we write it like this, we made a very important assumption that you need to be aware of. What is the assumption? The assumption is, actually there are two assumptions. First, that the length of the extent of this impulse response is sufficiently short and smooth with respect to the window of the short-time Fourier transform. That's why we move here from convolution to what we call MTF. MTF is multiplicative transfer function. And this is a very important thing to notice. Okay? So we assume that the impulse response is short, sufficiently short, relative to the length of the window of the short-time Fourier transform. So what we said, that sometimes you don't want to work with long window in the STFT, because you want to work with the window such that the signals can be approximated as stationary during that window. For example, for speech signals, we work roughly with 20, 30, 40, 50, even maybe sometimes 60 milliseconds. But the impulse response in the room, for example here, when I speak, if you put a microphone on when you listen to my speech, the impulse response in this room can be hundreds of milliseconds. So it's much longer than the length of the window. Of course, we can take longer window of the STFT, but this has a very, big disadvantages, because then during that window we cannot discriminate or identify different phonemes or different parts of the speech, because during that window the signal is non-stationary, is changing during hundreds of milliseconds. So what do we do? Okay? So instead of coming from here to here, you see, we need to do something else. YMTF. We can write it as GMTF convolution, and here the convolution is just along the time. Okay? So it's convolution in time with XTF plus VMTF, which means that we can write it as sum over tau GM tau F XT minus tau F plus VMTF. So this will be the model, which is very important. You see, it's a convolution in the time axis while f is fixed. So we don't use data from different frequencies. So it's like convolution. So this is called convolutive transfer function in the STFT domain. So it's convolutive because we use convolution. So what you can do is to take, even if you work in the STFT domain, you can process signals for each frequency, and then we need to take some windows, okay, additional windows. And we can take for each, so for each sensor, we can take L windows, such that we can approximate this convolution. And then we concatenate these L windows of M sensors. So we get a vector. So here, remember in the time domain, we worked with a vector. Okay, so we defined a vector of length ml by 1. So this is the vector of measurement. Why? Because we took L samples from each sensor and we concatenate them of all the sensors, and we work with vectors of length ml in the time domain, multi-channel. Okay, we work with multi-channel. This is in the time domain. In the frequency domain, with this, okay, we worked with vectors of length m. Okay? So these vectors, we worked with this, and the filters also. The filters here, it's length ml. So we work with filters of length ml. Here we worked with filters of length m. And when we moved, we talked about extension or implementation in the STFT domain. So if we use the MTF approximation, the multiplicative transfer function approximation, this is approximation of this model. Generally, it's not correct mathematically. It's an approximation which can be satisfied when the impulse response is short compared to the window. So when we have short impulse responses, so we have just a few reflections. We don't have many reflections and reverberation. So under the MTF approximation, we can also work similarly to the Fourier transform. So we can work with filters of length m. So we work with filters of length m for each frequency. Okay? And how many frequencies do we have? So if the length of the window is L in the STFT domain, if we have L, the length of the window is L, so we have here L, also here, if we have L frequencies, so we have L filters of length M. You see all of that connection? Very nice. So here we worked with long filters of length ML. In the frequency domain and in the STFT domain with the MTF approximation, which is very similar, we work with L filters of length M. So the problem, or all the derivations of the optimal filters is much simpler, because it's much simpler to work with smaller matrices of m by m. The coherence function, the coherence matrices are much smaller, of size m by m. So we split the problem of finding the optimal filter of length ml into L problems of finding filters of length m with this, okay, either in the Fourier transform or the STFT. That's why it's efficient or much simpler to work in the Fourier transform or the STFT. Okay? Now, if we work with, if the MTF approximation is not good, when the impulse response is much longer reverberation, in a room like this, the reverberation can be like a few hundred milliseconds. And then we can work with the CTF, convolutive transfer function approximation. So we choose along each frequency a certain number of windows. Let's call it L prime, L prime windows. And we have frequencies, which is the same, M frequencies. No, sorry. M is the number of sensors, okay? So for each frequency. So we have L prime windows along, for each frequency, L prime windows. And then we have M sensors. So the length of the measurement for each, the number of samples that we take for each frequency will be ML prime. And L prime is much smaller than L here. Why? Because here L is relative or proportional to the length of what we need, the length of the filters. And the length of the filters should be at least the length of the impulse response, or sometimes we can use shorter length because we work with relative transfer functions or relative impulse responses. But L here is long. But if L here is long, as we choose a certain length, L prime is roughly L divided by the jumps or the hops between different windows of the STFT. Okay? So for example, if we take STFT with 50% overlap, so we divide L by L divided by 2. Okay? So it will be 2. If we take overlap of 75%, so it will be L divided by 4, which will, so you see the number of windows L is roughly very small. Another thing, we need to take back windows, so it's not sufficient to take 4. So we need to take, because it will be non-causal, we have to take because of the overlap. So usually we take 1.5 times of this one. So we multiply it. We take at least something like that, 1.5 times of L, depending on the overlap. So if the overlap is 75%, we take 1.5 times of this. So usually we take something, if the overlap between windows in the STFT is like 75%, which is a common practice to take 75% or 50%. So we take like 6 windows here. So the length of the vector of measurements that we take, that we process, is about 6 multiplied with M, the number of sensors. And also, you see here, tau, it doesn't start from 0. It can start from -1, -2, depending on the overlap. So with 75% overlap, sometimes we start with tau -2. So it can be from -2 to 4. So pay attention to these important details when you implement or you work with a problem and you want to implement it in the STFT domain. This is very, very important. How you choose, how you define the problem. Okay, so we took this problem of finding filters of length ML. So here it's L problems of finding filters of length M. Here it's L problems of finding filters of size of length ML prime. But L prime is small, so it's not a big problem. And actually, if L is large, suppose that L is let's give an example. Suppose that L, it's like maybe 100, maybe even more. And we work with 10 sensors. Okay, so suppose that L is 100 and M equals to 10 sensors. So here, the length of the filters is 1,000. So we work with matrices, correlation matrices, 1,000 by 1,000, which is large. And it can be even larger if L increases, if we take here something else. So here, we solve 100 smaller problems. So we find 100 filters of length 10. And we work with correlation matrices of size 10 by 10. It's a huge advantage. Here, suppose that L prime is 6, even with this approximation, the CTF. So we will work with 6 by M, okay, so 60, which is still large, but it enables us to work with smaller problems, okay? Especially if L is large. Maybe it can be even 1,000. Think about it. Even if it's thousands, here still we work with matrices of filters to find filters of length 60. Instead of here, like 1,000 by 10, so 10,000, which is very large filters, very large correlation matrices, so on. So that's why we have a big advantage of working in the STFT, but we need to make sure that we can work with the MTF. If the MTF approximation is inaccurate, you need to extend it to CTF, and then it's a little bit more complicated, but it's important. And this is very useful in many problems, that the MTF approximation is not doing sufficient work. Any question? So this is a comment when we talked about the practical implementation. Now, so we go back to the frequency domain, okay? And because this is much simpler way to work, because you see when we extend here, actually, so it looks like that we need to define a vector of ML prime. It's very similar to the way we work in the time domain, but we do it for each frequency separately. Okay? So the methods that we worked in the time domain, we can use it in the STFT domain. So we combine the methods of the frequency domain and the methods in the time domains when we work with the CTF approximation. This is the convolutive transfer function model. Okay? If you want material, I can give you very nice papers that talk about linear models in the time frequency in the STFT domain, and they talk about MTF approximation and CTF approximation. Okay? They are very nice papers. If you like to read about it, I can provide to you. Okay. Now, we talked about the differences between signal enhancement and beamforming. Okay, so what does it mean? I talk about the main difference when you try to do signal enhancement compared to beamforming. So first, the most important difference that with signal enhancement, you assume that you can estimate or you know the relative transfer function or the relative impulse responses, the same. Okay? So what does it mean? It means that our model looks like this. Y MF is written by the desired signal in the reference sensor multiplied with some value. And this value is the correlation between x1 and xm. Okay, like this. This is the partially normalized correlation. We defined it, okay? So we have here plus noise. Okay. So for signal enhancement, we show that this is actually relative transfer function between xm and x1. Okay, so this is the relative. Actually, this can be written as this equals to GMF divided by G1 F. So if we take x1, we divide by G1, we obtain xf. Multiplied by gm, we get xm. So it's like this, see? But we assume that this relative transfer function, we can estimate, we can obtain it some way. And then, because we have this information, we can estimate the desired signal in the reference sensor. So we can obtain an estimate, which is an estimate of the desired signal for frequency f in the reference sensor, using this vector of measurements, a vector of length m. So we can find a filter of length m that we apply to the m measurement for frequency f, m measurements that are obtained from the m sensors, and we apply the filter to these m measurements, and we get an estimate of the desired signal. This is signal enhancement. So we need to know information about these relative transfer functions and the correlation matrix of the noise. For each frequency, we work with each frequency. Okay, we're done. So here we work with each frequency. And of course, you can do that STFT, MTF, or CTF. Okay, but I'm not going to work further with this approximation because the extension is quite straightforward. You are familiar with the time domain and frequency domain, so you can extend it to any model that you choose. Now, beamforming, the difference with beamforming is that we don't work with relative transfer function. We work with directions. So either you are in environment without any reflections, or you are in environment with reflections, impulse responses and transfer functions, but you assume that you don't know anything about the impulse responses or the transfer functions. You don't try to estimate them. You work with directions. So with beamforming, the model will be Y MF equals to X1 F multiplied with, like, instead of relative transfer function, we take the value of the direction, okay? So it can be written like this, d f cosine theta d. So theta d will be the direction of the desired source, and this will be something similar to relative transfer function when we don't have reflections. So it's just exponent. It's actually, it corresponds to delay. See, because if you have a sensor, delay when you transform into the frequency domain. So it's just phase difference. Because if you have a signal, a source that propagates and hits or propagates to a sensor array, and this is the observed signal, the desired signal in the reference sensor. So the desired signal in reference number m will be just delay, either plus or minus, so depending if it's before, if it hits that m sensor before or after. Okay, so delay in the frequency domain is just phase difference plus noise. So this is beamforming problem. This is the only difference between beamforming and signal enhancement. Now, okay, so this is signal enhancement, and it's multi-channel, okay? And this is beamforming. Okay, signal enhancement. Let me delete here. So signal enhancement. So we find a filter that is multiplied with the m measurements for each frequency. So this is called filter, okay, or so this is the filter that we try to estimate, the desired signal, using these noisy measurements. Here, also, we can say that we try to find z, but also I will talk what is z, okay? Just a minute. And we apply a beamformer to the vector of measurements. So here we call it filter, here we call it beamformer. Why? Because here we know we apply it to a direction, because we want that the signal that comes from a certain direction will be, for example, undistorted. So here we need to apply requirement that if h is applied to the steering vector, if h is applied, the beamformer is applied to the steering vector like this, vector d f. By the way, here you need to add m, okay? So this is the m element of the steering vector. So add here m. So if we apply the beamformer to the steering vector, which contains all the m components here, theta d, it is required that it will be 1, so we have distortionless response of the array towards a certain direction, theta d. This is beamforming. Okay, but you see, it's very similar. So the methods also are similar. Here, we don't necessarily use this constraint unless we want to work with MVDR or LCMV. with distortionless responses. Okay? So we add something similar to that. So H that is applied to the vector of the relative transfer functions, we require that it will be 1 if we want to work with MVDR or LCMV or GSC, just like we saw that it's equivalent. Any questions? Here, signal cancellation happens. Okay. Here, of course, if the signal comes from a certain direction, from theta d, and you keep it without distortion because of this requirement, so the direct path will remain unchanged. Okay? And usually we will get some reduction of the noise. Okay? But suppose that we don't have noise. And we have some reflections from surfaces. So here, we combine, using this filter, we combine the direct path and we combine the reflections into a stronger signal. Here, we suppress the reflections, we don't combine it with the direct path. So here, suppose that we don't have noise. We have less signal in a reverberant environment than we can have here. But of course, if the direct path is the dominant part of the signal, the reflections, let's say that they are insignificant, or they are very small. And so, so we have the signal, so we have less signal in this part, okay? But the reduction of the reflections, maybe it's not that significant. And in both cases, we can reduce noise. But it's not the same. Because here we will reduce noise that doesn't come from this direction. So if we don't know what is the noise, we try to reduce noise from all directions. Diffuse noise. Here, we can reduce noise that at least if its relative transfer function, if the correlation is different than the correlations in X1. I'll give you an example. Suppose that you have a source, desired source. I have an array here, desired source here, and a noise source in the same direction, but is a different position. Okay? Nice example, right? If we work with beamformer, we direct the beamformer towards the direction of the desired source. We cannot separate them. But here, what we can do is that what we can do is to identify the differences in correlations and then suppress this direction, the direction towards the source, and obtain the source from a reflection. And the reflection of the source with a certain surface is different because it's here. And the noise, maybe it's in the same direction, but it's in a different position, and the reflection will be different. So I'm talking about sources in the room, but it's also possible with radar or something like that. So if the direct path, the direction towards the desired source and the interference is the same, maybe because they are in different positions, the pattern of reflections is different. And here we can distinguish between both of them, and we can separate them. Here with beamformer, we cannot, because we don't take any reflections into account. Okay? So this is a big difference, but the methods, once you define the model, we can work with similar methods, okay? Similar methods in the frequency domain or in the STFT domain, because we can work just like we defined yesterday. But okay, but beamforming, in general, we have two different methods or family of methods, two different categories of beamformers. One is fixed and one is adaptive, okay? And there are differences in these two methods. Okay, with fixed beamforming, let's delete, okay, so I delete this part, okay? With fixed beamforming, I don't know the environment, which means I don't know the environment, I don't know the relative transfer function, this is beamforming. I don't know the statistics of the signal, so I don't know the variance of the signal in fixed beamforming. I don't know also the information about the noise. I only know that the desired source comes from this direction, and maybe I have undesired interferences from certain directions. So I know only information about directions, the direction of the desired source, and maybe directions of undesired interferences. But I don't know if the noise, what type of noise, what is the statistic, correlation matrices, and so on. So I don't work with these correlation matrices of the noise and the desired source. I don't work with correlation matrices of such. So with fixed beamforming, what I use theta d, okay, also I use the vector, the steering vector for each frequency theta d. So it's about, I know the direction of the desired source, and maybe I know some directions of interferences, but I don't know what type of noise, so I work either with white performance measures of white noise gain or directivity factor or combination, which means that I assume that the noise is spatially white, or the noise is diffused, or combination. Because I don't make assumptions about the noise. I don't know if what will happen in a practical environment because I design it offline, outside the environment. I don't make assumptions about the environment. So fixed beamforming, the advantage is that it will perform equally for different environments because you don't make assumptions about the environment. It doesn't adapt to the environment. But still, I need to know, or I need to assume that I know the direction of the desired source because I have some steering. I steer the beamformer towards a certain direction. With adaptive beamformer, I assume that I know information not only about the direction, so I assume that I know d f cosine theta d. I also know information, maybe I have information about the signal, the desired source. So sometimes I also know the variance of x1. I know the variance of the desired source in the reference channel. It's very nice information that I can use. I also know the correlation matrix of the noise. Here, the correlation, M by M. So it means that I know a lot of information with adaptive filtering. Actually, I don't know it exactly. I need to estimate. So I need to track, to follow, to do adaptive. In order to do adaptive beamforming, I always estimate. I estimate the direction, I estimate the variance of the desired source in the reference channel, I estimate the correlation. I update these values. So I have actually all the time I have updates, updated variables, so I estimate them. Okay. So here I can try, in this case, I can try to find an estimate of the desired source, actually. So if I actually estimate the desired source using a beamformer that is applied to the noisy measurements, then what's the difference between adaptive beamforming and signal enhancement? What's the difference? What do you think? What's the difference? One difference. One difference. What? Exactly. Exactly. So the difference between adaptive beamforming and signal enhancement is here I assume direction. You see, here I assume a certain direction. Here I assume, or I try to find the relative transfer function. This is the difference. So here I need the correlation matrix. Here I need the correlation matrix, phi x, or actually I need the steering vector. I need the steering vector, which takes into account not only the direct path, but all the reflections. Okay? So when I track movements of the source, because of the source, I track it. Or I track because of the movement of the array, I need to track the relative transfer functions. And then I call it signal enhancement. But with adaptive beamforming, I only track the direction. And of course, I need to estimate these two. So this is the difference. Now I can tell you, now that you know this difference, ask people who work in array processing if they understand this difference. Okay, ask them, what's the difference between adaptive beamforming and multi-channel signal enhancement? Okay, so it's not that obvious. But now you know the differences between multi-channel signal enhancement, fixed beamforming, and adaptive beamforming. So these differences are very important because sometimes we don't understand, okay, when do we get better performance with this or with this one or with this one? What are the differences? Now things are clear, which is very important. And once things like this, the differences are clear, we can take methods from one to the others. Okay? So we will have 10 minutes break, and then we will see the differences in performance after we understand the differences in the signal model. And what we know, we will talk about differences between these three. Okay? We will talk about differences in performance measures and also differences in the optimal filters or optimal beamformers. Okay? We take a high view of the relations between them. Okay? 10 minutes break, we continue from here. Any questions before we go to break? Yes. Okay, so it depends. Actually, every application that I showed, and you can think, Uh, so any application like this, it combines sometimes many things. And sometimes people who design devices, for example, smart glasses, you can think, which methods should I use for smart glasses? Suppose that I want to listen to somebody and enhance its signal. Okay? So here, you will need to estimate the relative transfer functions. But maybe these relative transfer functions are very difficult because if I move my head, these relative transfer functions change significantly. And maybe it's difficult to estimate them in an accurate way. Okay? So suppose that I know the information, everything I know accurately. If I know things accurately, I will use multi-channel signal enhancement because this will provide me the best performance. But when you estimate things that you assume that you know in the model, but in practice you don't know them, you need to include algorithms to estimate them. So for smart glasses, to estimate the relative transfer function, it's very difficult. So you say, no, it's too difficult. I will just estimate or track the direction of the source, like here. But then you think, even estimation of the source direction like this, when I move my head, or maybe the source moves, maybe I don't want to do that. Maybe I will just assume a certain direction, and it will be fixed. Okay? So when I look forward, I will fix like the source is in a certain direction. So if the person moves, I will not hear it, or it will be suppressed. So the person can move his head towards the desired source, which makes sense, right? So maybe I want to use fixed beamformer. But then, fixed beamformer, I need to assume certain noise field. Maybe spatially white, maybe diffuse, maybe combination. I don't know the spatial field of the noise field. So do I want to add another algorithm to estimate the variance of the correlation matrix of the noise? If I can afford to add this estimation, it's an additional algorithm. So I will use it. And then it will be adaptive in that sense. But maybe theta, I will use a fixed direction of the source. I will not change it. I will not track it. I will assume a certain direction. So you see, there are many combinations. If I cannot afford, because of complexity, to estimate this, and I cannot afford to estimate the direction of the source, I will use fixed one and certain noise that I think it's reasonable. Some combination of diffuse or some combination or maybe cylindrical noise field. So it depends. Maybe I will have some measurements in different surroundings, and I will say, okay, so this is like training data. I will use the same average noise field. Or maybe I can classify the noise field according to some small amount of measurement instead of estimating the correlation matrices. You see, so in practice, when you work on devices, things are more complicated because you need to add, but you need also to understand what kind of information I can use. If I want to add this information, or I would like to make assumptions, and so on. And you have some trade-off between the complexity, so how much information you want to add and estimate, and the error, because when you include additional information, you need to estimate it. And if you don't estimate that information accurately, you add more error. And maybe it's, maybe adding this kind of information which is not accurate, it doesn't improve the performance. So why to try to estimate it? Maybe you don't have time to estimate. You don't have the computational resources, or memory and so on. Okay? That's why it makes our life, interesting. If everything, you take the simple things, simple models, and you can solve everything, so we will find another job, Okay? So if you understand this material, and you understand what you can do, what are the options, you need to think what is the most beneficial way to solve practical problems. But practical problems are always more interesting. But in order to address practical problems, you need to understand the fundamentals of the methods and the differences. More questions? Okay, so we finished the break. So let's continue. No, just a minute. Okay, so let's have 10 minutes break. We will continue. We will continue here. Okay, let's take this one.
Our world is more digitally connected than ever before, and emerging technologies promise to amplify this connection. Devices like smartphones, smartwatches, tablets, and laptops connect to Wi-Fi networks to provide instant access to information and entertainment, and that connection is made possible through signal processing. For Wi-Fi to work successfully, signal processing is used to overcome two main challenges: determining which devices can be active at all times, and decoding the information bits that are transmitted over the air. A household typically has only one form of internet connection, whether it be DSL, cable, or fiber optic, but has multiple devices talking to the same router. If you enjoy watching TV while also scrolling through your favorite apps on your smartphone, these devices must send signals to the same router to access information. To avoid the signals from colliding, Carrier Sensing Multiple Access, or CSMA, is used. CSMA forces every Wi-Fi device to be polite, meaning they observe the radio spectrum and sense whether a channel is available for it to use. When a Wi-Fi device occupies a channel, it specifies how long it needs the channel for, which allows other Wi-Fi devices to determine when the channel will be free. So, while someone might stream video on their laptop and use their smartphone at the same time, it's the unseen rapid transfer of channel access in the airwaves that allows the use of both devices simultaneously and without interruption. But channel availability is only one step of successfully transmitting Wi-Fi signals. In an ideal situation, there is only one direct path between a device and the router, or direct line of sight. But signals can also be deflected off of the surrounding environments like walls, floors, and ceilings, creating multi-path channels. Each of these paths will have a slightly different delay, and the different delays in multiple paths cause signals to become entangled in the time domain. Signal processing engineers overcome this by using a technology called orthogonal frequency division multiplexing, or OFDM, that utilizes the concepts of time and frequency in signal processing. These frequencies are obtained by the fast Fourier transform, an algorithm that efficiently converts signals from the time domain to the frequency domain, and vice versa. Any signal can be represented by the sum of a very large number of sinusoidal waves having different frequencies. Think about the frequency domain as you would a piano. Each note represents a different frequency, but if you play a C note, the pitch you hear will always be a C note regardless of any reflection paths the sound takes. The fast Fourier transform enables OFDM to digitally decompose the multipath channel by dividing the bandwidth into small subbands, each carrying a different data stream. Because these subbands live in the frequency domain, the interference amongst the data streams is eliminated, thus avoiding the signal entangling problem in the time domain. As our world becomes even more digitally connected, future Wi-Fi devices will utilize multiple antennas and larger bandwidth. We need signal processing engineers to overcome new challenges that we have yet to face. Are you ready to solve them? Learn more through the Signal Processing for Communications and Networking Technical Committee of the IEEE Signal Processing Society.
Okay, so what I wanted to show you that in different areas, signal processing people working in different areas, sometimes they use models and they call different things different terms. So when you understand the things and you learn or you combine, don't be afraid to read signal processing problems from different fields. Maybe the terms are different, but maybe they mean similar things, and you can see the problems, how they define, what kind of assumptions they make, and so on. So you can learn from other fields in signal processing, and you can combine different methods, different tools for problems that you will face at work or research, okay? So it's very important that don't constrain yourself to the area that you work. For example, if you work with multi-channel or underwater communication, okay? Or beamforming, or speech processing, things. Don't read only the material in that area. Be aware of other areas which are relevant, because people may do very nice work in different areas, but because you're not familiar with the terms, maybe you say, oh, it's not relevant to me, it's different. But maybe you can gain out of it insights that is relevant to your topic, okay? So expose yourself and don't be afraid to read from other areas. Many things, just like I show you, communication, Wi-Fi, underwater, in different environments, radar, sonar, seismology. Many things have things in common, many areas. If you take a look on my website, you will see papers in sleep monitoring. How is it related? In speech processing, of course. Some works in radar, underwater processing, image processing, seismology, sonar, things like that. So you can see how do I publish in these so many areas? Because things are relevant and there is much overlap. When you understand the basic, the mathematics behind it, many things have similarities, okay? So I wanted to encourage you. Okay, so now let's see the overlap between these problems and the differences, okay? So I will give you a reminder with the first. We talked, if you remember about signal enhancement, I will repeat the performance measures, okay? Very quickly, performance measures and optimal filters, okay? And then I will talk about performance measures and optimal beamformers for the fixed beamformers, performance measures and optimal beamformers for the adaptive beamformers, okay? And then we will see how we compare the performances of these filters and beamformers, okay? But first, let's see the performance measures and the optimal filters or beamformers to see the difference. Okay, so let's go to the multi-channel signal enhancement. So we have performance measures. Okay, so we define the performance measures. I go over it quickly because I don't need to go over the formula. I just want you to remember. Okay, so we talked with the multi-channel enhancement in the frequency domain. We talked about signal to noise ratio. Of course, the input and the output and the gain in SNR. Okay, because when we filter a signal, we try to estimate it. So we can talk about the gain in SNR. The gain in SNR compared to the reference channel, which is the array gain. Okay? So we talked about the array gain for signal enhancement. Then we talked about noise reduction factor, how much noise we reduce, and how much is the desired signal reduction factor, how much we reduce or distort the desired signal, and the desired signal distortion, distortion index, because we want to see the normalized difference between the estimate of x1 and x1. And we normalized its variance, the error, by the variance of x1. And then we talked about mean squared error. We remember all of that. Okay. So when we talked about signal to noise ratio, we can find a filter that maximizes the SNR. When we talk about the mean squared error, we can find a filter that minimizes the mean squared error, the Wiener filter. And then we said if we have the mean squared error, which is, we can split it into two components of mean squared error of the distortion and mean squared error of the noise with the residual noise, the variance of the residual noise. So we can add a trade-off filter. So if we go to the optimal filters, okay, so we have the maximum SNR, the filter that maximizes the SNR, the Wiener, and we have a trade-off filter that we can trade off using the parameter mu. We can trade off or find a trade-off between noise reduction and distortion. And if we don't want distortion at all, then we have the MVDR. So we reduce noise in the noise-only space. And then we have also the LCMV. The LCMV, in terms of output SNR, is the less optimal than the MVDR, but if we know that we have another interference, which in terms of noise power is not that significant, maybe its power is weak. So we want to give that source more weight. We want to reduce it, even though it's weak, because maybe it's some non-stationarity, some clicks, or some interference that interfere with our system. Okay? So we have multiple things, and even something weak, sometimes it interferes in our estimate of the desired signal. So we add an additional constraint, to the MVDR. The MVDR has one constraint, distortionless response. For LCMV, we have additional relative transfer functions that are related to the noise, to noise sources. And for these noise sources, we want maybe to put them, to completely eliminate them. So we add some constraints on interferences in the LCMV. So obviously, because we add constraints, the output SNR will be lower than the MVDR, but at least we're able to eliminate weak noise sources, which are very significant, not in terms of the power, but in by other type, or maybe according to their characteristics or something else. So we still want to cancel them, okay? And then we talked about generalized side lobe canceller structure that actually enables us to implement LCMV and MVDR by using adaptive filtering. We talked about adaptive filtering and their advantages in real implementations, real problems. Okay, so this is with signal enhancement. Now let's move to fixed beamforming. Okay, so fixed beamforming, performance measures, and optimal filters. Okay, so let's talk about fixed beamforming. Okay, so performance measures here. So with fixed beamforming, the performance measures are very limited because we don't know, or we don't assume, we don't try to estimate a lot of information. So we don't try to estimate the signal. So something like MSE, mean squared error, something like distortion index is irrelevant. So the only things that we try to find or we formulated are beam pattern, which is important, beam pattern, because it tells us that a signal, any signal that comes from any direction, how strong will it be at the output of the beamformer, at the output of the beamformer? How strong will be present at the output of the beamformer? So actually what we want is that the desired signal, or signal that comes from theta d, we assume that we know the desired direction. So a signal that comes from theta d will be undistorted, like this. And signals that come from other directions, which are undesired, will be suppressed as much as possible. Oh, but of course, we cannot do that. We cannot suppress any signal that comes from any other direction. So the beam pattern shows us, it gives us what is for example, the power of a signal that comes from any direction, theta. And usually what we want is to have a peak at the direction theta d and very small side lobes from other directions. And we also talked about the dependence of the width of the main beam on frequency. So when the frequency increases, the main beam becomes more narrow for a given array. In addition, so we can design constant beam width beamformers. We can try to do that. There are some methods. So we can actually try to design a beam pattern, a desired beam pattern. So somebody tells us, I want this beam pattern. So I can design, what does it mean to design the beamformer? To design this H for each frequency. This beamformer contains M elements for each frequency. So we can try to find these weights, this beamformer, such that we will get a desired beam pattern. So this is an important performance measure that we didn't encounter for signal enhancement. For signal enhancement, we don't care. We care about other things because we estimate the signal. Here, with beamforming, we care about the beam pattern instead, because we want how we design the beamformer. So what happens for different directions? Here we don't deal with the directions. We deal with relative transfer functions, which depends on the environment, the position of the source, the position of the reflections, and so on. Okay? And then we talk about signal-to-noise ratio. So we have input SNR, output SNR, and the gain in SNR. The gain in SNR, it means how much the SNR at the output of the beamformer is relative to the input of the input SNR, which is the signal-to-noise ratio at the reference sensor. So the gain in SNR, we give two different definitions. Because the gain in SNR depends on the noise environment. So if we don't know the noise environment, how can we define gain in SNR? We don't know the signal, we don't know the environment. So how can we define gain in SNR? So we see that using a beamformer, we don't need to know the signal or the variance of the signal. We just need to know what is the response to the direction of the desired source. So we use this constraint that it's 1. So any signal that comes exactly from theta d will not be distorted. And then the noise, regarding the noise, we assume a certain noise. So we can assume either the noise is white or the noise is diffused. So if the noise is white, the gain under the condition that the noise is white, it's called white noise gain. If the noise is diffused, so the array gain when the noise is diffused is called directivity factor. So obviously, we would like to have high gain, high array gain under all conditions. When the noise is white, when the noise is diffused, or any other noise field. But we showed that we cannot do that. If we design the beamformer to maximize the white noise gain, the directivity factor will be lower. If we design it to maximize the directivity factor, the white noise gain will be lower. So we need to find a trade-off, just like trade-off that we worked for signal enhancement. So we found a trade-off. Trade-off between what? Signal enhancement. Trade-off between what? Two, exactly, signal distortion and noise reduction. So here, with fixed beamforming, we will show that we can find a parameter that controls the trade-off between white noise gain and directivity factor. We cannot talk about distortion, okay? We talk about white noise gain and directivity factor. So if we try to reduce, okay, with white noise gain, if we want high white noise gain, it means that we suppress white noise. With directivity factor, high directivity factor, it means that we suppress diffuse noise. Or we try to suppress noise that comes from unknown direction. Also, something like that. Okay? So sometimes if we don't know the direction, we assume that all directions are equally probable. So all directions of the noise are equally probable, so we try to reduce them, like if there is noise from all directions, because we don't know. So this is the directivity factor. So if we try to reduce the diffuse noise as much as possible, we will get some amplification of white noise. And this is very important. It means that if we design a beamformer and then it amplifies the white noise, especially in the low frequencies, so it will affect the output. So at the output of the beamformer, we will get high white noise because it is amplified compared to a single sensor. So this is a big disadvantage of just maximizing the directivity factor. It doesn't work well. So we found fixed beamformers. Either, yesterday we talked about the beamformer that maximizes the white noise gain, or beamformer that maximizes the directivity factor. So now we would like to find a fixed beamformer that achieves some trade-off between them, one at the account of the other. Okay? But now, because it's fresh, I don't want to just continue here with the fixed beamformers method. okay, before. So I'll give you some discussion about the performance measures and the type of beamformers that we achieve with adaptive beamforming. Okay, before we continue. So you have more high-level view of the differences. Okay? So let's go to the adaptive beamformer and see what are the performance measures and the methods that we use for optimal beamformers, optimal adaptive beamformers. So let's jump forward to adaptive beamforming and talk about the performance measures. So here we assume, I don't want you to look at the expressions. We will go over it. Don't worry. When you understand everything, will be clear. So I just want you to look at the definitions here, performance measure. So of course we can talk about signal-to-noise ratio because we assume that the desired signal comes from a certain direction, and we know the correlation matrix of the noise. We know the noise environment. But we assume there are no reflections. We assume free field, no reflections, because we have only directions. So in a free field, the noise or the signal-to-noise ratio, it's correct, or the array gain is correct. If you take it to a practical or environment with reflections, it's incorrect. Okay? So there will be difference. Okay? So when we try to optimize the beamformer, we optimize it for a certain environment with no reflections. If we eventually have reflections, of course, the performance will be different. Okay? So this is the signal-to-noise ratio. So we can try to find a beamformer that maximizes the gain in SNR. Okay? And we can define the noise reduction factor. Also, the noise, we assume free field, free environment. But we know the noise field. We know the correlation matrix of the noise. So we can define noise reduction factor. We can define desired signal reduction factor, desired signal distortion index, mean squared error. But all these are true. These performance measures are true and defined for environment without any reflections. And now that we define these performance measures, we can find adaptive beamformers that optimize these performance measures. Let's see what type of beamformers we can have. Okay. Adaptive beamformers. So because we can define the mean squared error, we can find a beamformer that minimizes the mean squared error. So we will find the Wiener beamformer. But the Wiener beamformer will be correct for environment without reflections, free field. But you see, here we have Wiener beamformer, here we have a Wiener filter. They're similar. Just here we need to find the relative transfer function. Here we design it for free field, free from reflections, free field environment. This is the difference. But the expressions will be similar. Instead of this correlation, or instead of the steering vector that is obtained from relative transfer functions, we will have a steering vector based on the direction only, without taking into account reflections in the environment. Okay? Wiener filter. Then also we have MVDR. No distortion in the environment with no reflections. If the environment that we assume here, actually it contains some reflections, of course, we can get some distortion. It's okay. But we design everything with beamforming for free field, no reflections. So we have MVDR, trade-off, maximum array gain, okay? Maximum SNR, it's array gain, and LCMV. These methods are similar to signal enhancement. Just the difference, instead of the steering vector, which is based on the relative transfer function, we will use steering vector for directions. No reflections in the environment. See, so all these expressions will be very similar. But we can also verify what happens to the beam pattern and so on. Okay, here we don't work with beam pattern. Here we work with beam pattern. So we can see what happens to the beam patterns for different adaptive optimal filters. Okay, so this is very important. Any question? Okay, questions? Okay, very good. So now you are ready for the fourth and last assignment. Okay, let's go with the fixed beamforming. We reached. So we talked about delay and sum and maximum. Here, we came to here. We compared, we showed examples to compare delay and sum beamformer, which maximizes the white noise gain, and the maximum DF beamformer, which maximizes the directivity factor. We showed examples, and we showed how the beam patterns look like, what is aliasing, what happens, how come when we increase the frequency, sometimes the directivity is reduced. We showed this example, that the directivity can become lower when we increase the frequency. This is indication of aliasing. We talked about aliasing, what happens, and so on. So your fourth and last assignment. If you like more assignments, I can send you when I return to Israel. Actually, you have as many assignments that you want. Any example that I show, you can repeat that, you can play, you can change the signals. And also, at the end of each book chapter, you have many problems. So you can try to solve it. And in addition, you can read some of the papers I cite at the end of each topic. So you can read some of the papers, which are very interesting. Okay, so you have enough work to do as much as you want. So this assignment, it's relatively short because tomorrow we finish. So it's quite short, but it's important. Okay, so it will not take you much time. Now, let's continue. So we continue with optimal beamformers for fixed beamforming. Okay, so when we found the maximum DF beamformer, so the performance of the max DF beamformer depends on theta D. Okay, so let's delete here. Actually, sometimes people that work in this area, array processing, you ask them, try to ask them, what is the difference between maximum DF beamformer and super directive beamformer? Okay? What is the difference? So sometimes people, they don't understand the difference, and very shortly, you will know the difference. You can check if somebody, so I can give you afterwards some quiz with differences. But now you see the differences. Okay, so what is the difference between max DF beamformer and super directive beamformer? It looks like that, okay. We have the model, okay? So we can find a beamformer that maximizes the directivity factor, okay? So what is the directivity factor? Directivity factor is the array gain when the noise is diffuse, okay? So if I write the array gain for a given beamformer, this is the array gain, which is obtained as HF D F cosine theta D magnitude squared divided by HF gamma, we call it gamma 0 pi in the slides, but actually this is the normalized correlation matrix of diffuse noise for the frequency f. Okay? So this is actually gamma v divided by gamma v1. This is the normalized correlation matrix, HF. This is the array gain for diffuse noise. Because here we put the normalized correlation matrix of diffuse noise. If we put another one, so it's array gain for the environment. But for fixed beamformer, we need to assume a certain noise field, either this or combination or whatever. So if we use this, we call it directivity factor, because here we have the correlation, normalized correlation matrix of diffuse. So this is directivity factor. Now, suppose that I try to maximize this. So we try to find H, beamformer, that maximizes the directivity factor. Let's call it, okay, the directivity factor, subject to the constraint that we don't have distortion for any signal that comes from the direction theta d, which means that H d f cosine theta d equals to 1. So this is equivalent to minimizing the denominator. So we need to minimize HF, minimize over HF, H gamma 0 pi F HF, subject to the same constraint. Okay? Same. Now, suppose that we find, so how do we find this? We know how to solve this problem with the Lagrange multiplier. So the solution for this problem, we call it max df beamformer. So it looks like this, gamma 0 pi, this matrix, minus 1 d f cosine theta d divided by dh f cosine theta d gamma minus 1 0 pi f df cosine theta d. So if you do the assignment, the last assignment, actually it's very similar. So these kind of problems, you know the solution, straightforward solution, okay, using Lagrange multiplier. Once you prove it, you find many of the MVDR, directive, superdirect, and so on. So it's important that you know how to solve an optimization problem like that. So this is the filter that maximizes. So the maximum directivity that can be achieved, maximum directivity. So if I ask myself, okay, what is the maximum of the array gain, which is using this filter? Okay? So the array gain that is achieved using this max df filter, what do? I take this expression and I put it here. So what will it be? What is the expression? You see, the denominator is 1 because it satisfies the constraint. Denominator is 1. So it's actually only the denominator. Okay? So if I use this, what will I get? So I take this. Okay? And I have this h gamma, so I multiply here and take h from here. Okay? So it will be, you see, this is a number. Okay. So I get, if I put it here, so I get, okay, I don't want it to be, I will put it here. So it will be d h f cosine. By the way, here it's minus 1, okay? Here, please correct it. It's minus 1. No. No, it's like this, okay? Sorry, it's without minus 1. Okay. So if I put it here, cosine theta d, dh, gamma minus 1, put it here. So I multiply it with gamma, dh. Oh, okay, 1 over this. If I multiply it with h transpose conjugate, multiplied with gamma. Okay, so I have dh. This is symmetric matrix. I multiply it with this. And then again, so it cancels out. And then again, I take h, so I will get gamma minus 1 dh divided by square of this, and then I need to take 1 over, okay? So it will be okay, I will write it and then write minus 1. Okay, so it will be easier for us. Because I want only this term, and then I will take to the power of minus 1. So if I multiply here, so it's dh gamma minus 1. We multiply with gamma, so it cancels. And then I have, again, gamma minus 1 from here, d. So this is the denominator. And then the denominator is this value that comes from h and h. So I have square of this. dh f cosine theta d gamma 0 pi minus 1, this part, f dh f cosine theta d. Oh, I'm sorry. Like this. And this is square. And all of that to the power of minus 1. Okay, so you see the numerator, and here it's square. So it cancels. So I can remove this part with the square and take minus 1. So this is the maximum directivity factor that can be obtained using the max DF beamformer. So we get, okay, I will delete that. So it will equal to DHF cosine theta d gamma 0 pi to the power minus 1 f d f cosine theta d. Okay? So, of course, it depends on the frequency. Of course. So, for a certain frequency, the maximum directivity factor that can be obtained is by using the filter or beamformer that maximizes the directivity factor. Okay? So this is because this is called max DF beamformer. So using this max DF beamformer, if we put it in the array gain for diffuse noise, we get an expression of the directivity factor. Okay? So we can see that the directivity factor depends on the direction. What does it mean? It means that suppose that we have sensor array. Suppose that we have a sensor array. And so on. Okay? And we have direction. This is the direction, theta d. And this is the sensor array. So it can be uniform linear array or any other array. So do you agree that if I plot the array gain, so if I plot the array gain using H max df as a function of f, okay? So it will give me a plot. It will give me a plot how the directivity factor, the directivity factor depends on F. But theta D is given. Okay, so I will have a plot. Assume that, okay, it goes up with the directivity goes like this. Okay? But this is for a certain theta D. So assume that the desired source comes from this direction. And maybe for a different theta D, we will get something like this. For a different theta D, we'll get something this. Maybe. I don't know. So do you agree that this plot, how the directivity factor using the beamformer that maximizes the directivity factor, this plot depends on theta D. Where is the direction that I look for the desired source? So it depends on the direction of the desired source. Okay? You agree. We obtained explicit expression. So now I can ask a question. Suppose that I'm able to steer the array, to change the direction of the array. What does it mean? I can control also theta D. And now I can ask you a question. Suppose that I want to maximize the directivity factor that is obtained with the maximum directivity factor beamformer by steering the array relative to the desired source. So I want to change. Okay? Understood? I can steer the array. So I can change theta D. So maybe I can change the array such that theta D will be 0. Maybe I can change it such that theta D will be 45 degrees, 90 degrees. Because it depends on the array. So I ask, what is the steering of the array such that I maximize the directivity factor? So I hope that it will not depend on the frequency, because I cannot steer the array for each frequency. Okay? So if it depends on the frequency, I can take the integral here, overall frequency. Is it true that I will take an integral here? No. Okay? I need to do the integral at the numerator and denominator. Okay? But the denominator is, okay, so when I define the array gain, the integral of the numerator is the integral over 1. And this is the integral over the denominator. And this is the denominator. So I can take the integral here. You see? So generally, I cannot take integral of signal to noise ratio. But because the definition of the array gain, okay, the output SNR divided by the input SNR, okay? So you need to be careful if it's possible to take the integral, because actually when you take the output SNR, you need to take the integral separately of the numerator denominator. So you need to make sure how to take the integral, because sometimes terms cancel out. And we saw that when you talk about broadband definition, so if you take about broadband output SNR, you need to put the integral in the correct places before you cancel out. Okay? So make sure. But now let's assume that I want to maximize this directivity factor for a certain frequency. Or maybe I hope the result will not depend on the frequency, which is then I don't care about the frequency. So I mean that I want to steer the array such that I can control theta d. It's a good question, if I can do that. Think about the smart glasses. Smart glasses. Suppose that I want to maximize the directivity factor using array of sensor, array of microphones on the frame. And then I can ask, I want to design a fixed beamformer, assuming that the noise field is diffuse. And I design a beamformer that maximizes the directivity factor. So to which direction will I design it? To this, because I can steer the array. So I will design it towards this direction, maybe this direction. So when I want to maximize the received signal from this direction, I will look this direction maybe. Okay, so it doesn't make sense, right? Because if I look to somebody, I want to maximize this direction. So I will design it such that it will maximize it towards this direction. But in some applications, I don't care. I can steer the array mechanically. And so I can change theta d. And then I ask this question. So a beamformer, the maximum directivity factor beamformer, where you can control theta d such that this will be maximized, so we call it, so the argument of this will be theta 0. Okay, so it's some theta 0 that maximizes to steer. So if we get H max df for theta 0, so this beamformer that maximizes the df when theta d is theta 0, this is called H superdirective beamformer. Okay? Any questions? So let's talk about some application. Suppose that I have uniform linear array like this. So sometimes it can be shown that sometimes that the maximum directivity factor is obtained when the source comes from the end fire. So theta d is 0. So theta d is 0. So what I can do, I can take the array and direct it in such a way that it will be directed to the source. And you can see that also with, I don't know if you're familiar with shotgun microphone. Just journalists, they use to interview somebody. So they use a microphone array, which looks like a long microphone, but actually it's a microphone array. So it contains a few microphones. And they take the microphone array, and they don't put it like this, the microphone array in front of the speaker. They put it like this. So the source comes from the end fire. And why do they direct it like this? Because this microphone array is designed with a fixed beamformer such that and the maximum directivity factor is obtained for theta equals to 0. So they direct it towards the source, which is very nice now to understand, because they get super directivity. Super directivity, it means that we also control the steering of the array. And we obtain the maximum achievable directivity factor. Very nice. And actually, for this kind of array, the maximum directivity factor is obtained for theta equals to 0, theta d equals to 0, and it doesn't depend on the frequency, which is also nice. So for all, it maximizes the directivity factor for all frequencies. Questions? So we understand what is super directivity. So now you can ask people that work in the field, what is maximum directivity factor beamformer and what is super directive beamformer. Okay, it will be interesting to see the answers. Okay. Okay. So actually, for uniform linear array, this is the expression. Why? Oh, I forgot about the tea break. Okay. Sometimes I forget about breaks. I hope that you forget also. Okay. So it means that the material is interesting. Okay, so I will give you the break, but just 1 minute. So this is the expression of the beamformer, just like here, just like the maximum directivity beamformer. But here, because we use uniform linear array, you see that theta d is 0. And then that's why we say here 1. So cosine 0 is 1. So here is a particular beamformer of the maximum directivity beamformer by changing theta d to 0. But this is for uniform linear array, because theta d that equals to 0 maximizes the directivity factor. If the array is different, you have different sensors. So you need to find the theta d that maximizes the maximum directivity factor. Okay? Very interesting. It's beautiful, right? Okay, so let's have 10 minutes or how much you need because it's a tea break. So maybe 15 minutes, okay? And then we continue. Okay. So this is super directive beamformer. Now we understand. Okay? So it's very nice. And then we can move on to robust super directive. Actually, we can talk about robust anything. Robust maximum directivity factor, robust. Robust, it means that when we estimate some information, that it will be robust to error in that information. Okay? So robust super directive, it can be robust relative to a few things. When you talk about robustness, it means robustness regarding some errors. So the errors in this, what I'm going to talk, is error in the environment. So super directive beamformer, it means that we designed the beamformer that it will maximize the array gain for diffuse noise. But then, because of error, because of non-ideal sensors, we also have thermal noise. So because of the thermal noise, we will get amplification of the thermal noise at the output of the beamformer. So this is sensitivity to error. Okay? So we can talk about different types of error. And then when we try that something that we design in an optimal way, we define an optimization problem, and we make assumptions. Everything is accurate. And then we check the sensitivity of what we design, the optimal design. We check how it's sensitive to some errors in our assumptions. And we see that for some assumptions, it's very sensitive. Just like we showed that the maximum directivity factor beamformer, I'll show it here. Okay, the maximum directivity factor beamformer. So this is the white noise gain that we obtained with the maximum directivity beamformer. So we see that for this example, the white noise gain is very, very low. It means that we designed the beamformer to maximize the array gain in diffuse noise environment, but then because of thermal noise, it will not perform well. So if the environment actually, it doesn't contain, we have no thermal noise, maybe the sensors are ideal with known thermal noise, then we are good, no problem. Then we don't need to talk. You know, when you make assumptions and the assumptions all are good and correct, no errors, no need to talk about robust optimization. Robust optimization, it means that we make assumptions, but then the assumptions are not fully correct. So thermal noise here, we assumed when we design maximum directivity factor beamformer, we assume only diffuse noise. But then in practical environment, we also have thermal noise. And then we see that because the white noise gain is so low, it can come to minus tens of dB. Very, very low. It means that in practical environment, we will get amplification of the thermal noise at the output of the beamformer, which means that the maximum directivity beamformer is not robust to thermal noise because it cannot handle error such errors of thermal noise. So how do we deal with that? So we need to change the optimization problem such that it will perform, it will have some constraint or perform better when we have also white noise. So the solution to something like that is very easy, okay? How do we, so this is an approach that you can use for anything that you do in your research, anything that involves optimization. So instead of using this problem, you see, this optimization problem is to obtain the maximum directivity factor. So instead of this problem, I will add another constraint. Okay, I will add another constraint. So the white noise gain, let's call it the white noise gain, that is obtained using H, the filter, the beamformer. I want it to be larger, so I can add a log or something like that, okay, if you like. But I would like that it will be larger than a certain value, a certain threshold. So if I add this constraint or this requirement, it means that we know that this beamformer will achieve maximum directivity factor under these two constraints. So a signal that comes from theta d will not be distorted, and the white noise gain for the frequency f, for any frequency f, will be at least as large as W minimum. Very simple. So we change the optimization problem. But when we add constraint, so eventually we will reduce, we will get lower array gain. Because something, when we add constraint, the performance or this minimization will be less. So the directivity factor will be somewhat reduced. But it's okay, because we are willing, it's a trade-off. If we want to increase the white noise gain, we want to increase, especially in the low frequency, it means that the directivity factor in this frequency will be lower, because we added an additional constraint. This is the way to deal with robust optimization problems. So you can do that with any problem, okay? So how do we solve this? How do we solve this problem? Very easy, okay? So instead, let's call to the directivity, okay? So instead of maximizing the directivity is like minimizing 1 over the directivity, okay? I will write it like this. So we want to find H such that the directivity factor is minimized, okay? But instead of subject to this constraint, of course. Okay, I will write it. But instead of minimizing this, I can minimize this plus epsilon 1 over white noise gain. Something like this. And then I can write these expressions, the array gain for diffuse noise and the array gain for white noise gain, more specifically. Okay, so if what I did, when I have additional constraint, I can give them certain weight. Okay, subject to H df cosine theta d equals to 1. Okay? Now, if epsilon is 0, what does it mean? Not robust, what we did before. So it will maximize the directivity factor. If epsilon is larger than 0, if I increase it, the more that I increase this, I give more weight to this requirement. So when I increase epsilon, so I give more weight, so it will try more to minimize this. So it will maximize, it will increase the white noise gain. But then it will increase the white noise gain and will decrease the directivity factor. So epsilon is like a trade-off parameter to control between white noise gain and directivity factor. By the way, whenever you have trade-off between two things, you can add parameter. If I have three things, I can add another parameter. Okay? And the parameters control the weight, how much weight. Now, if I want to satisfy this constraint, I can choose epsilon for each frequency. I can put here epsilon as a function of frequency. And for each frequency, I can change this. I can change such that there will be equality here. So I increase the white noise gain until it reaches W minimum. So this parameter will depend on the frequency. Okay? Very easy. So let's see here. Let's see how we do it. Now that you understand, it's very simple. So suppose that I take the super directed beamformer, okay? And instead, I can write the directivity factor specifically. This is the array gain for diffuse noise. The array gain for diffuse noise is the directivity factor that is obtained using the beamformer H. I can write also the expression for the white noise gain. This is the array gain when the noise is white, spatially white. So I have here a matrix, which is identity matrix. So this is the expression for the white noise gain. And then I will try to minimize this. 1 divided by D plus epsilon, 1 divided by W, the white noise gain. So if I increase the Lagrange, this is a Lagrange multiplier. If I increase it, I give more weight to this part. So I will increase the white noise gain, but I will get lower directivity factor. Okay? So I can write it like this. So it's beautiful that I can find this expression. You see, this expression, when I add epsilon, it looks like this. You see? So this is a very nice expression. Why? Oh, there is a mistake here, -1, okay? Just a minute. Oh, no, it's okay, it's okay. Something like that. So it's a very nice expression. Why? Because the solution to minimize this under the distortionless constraint to the direction theta d, this is the solution. You see, so what we did here, instead of minimizing the directivity or maximizing the directivity factor, or minimizing 1 over the directivity factor, and then here we have a matrix, this matrix. Now we replace this matrix by this matrix. So this is the solution. Straightforward. You see, just like the maximum directivity factor, but instead of gamma 0 pi, which is the correlation matrix that corresponds diffuse noise, we have this matrix plus epsilon I, identity matrix of size m by n. So the solution, this is the solution. So this solution is more robust You see, it's very nice to see that it's robust because, as you know, when you invert a matrix which is singular, we know that the solution is not robust because when you have a matrix but which is close to be singular, maybe it's invertible, but it's close to be non-singular. How do we know if a matrix is close to be singular or not? Condition number. Yeah. What is the condition number of a matrix? Yeah. So all the eigenvalues of the matrix, it's a symmetric matrix, right? So all the eigenvalues are positive. So for a symmetric matrix, all the eigenvalues are positive. We take the ratio between the maximum eigenvalue divided by the minimum eigenvalue. This ratio is the condition number of the symmetric matrix. If it's large, it means that the smallest eigenvalue is small compared to the maximum. So if this ratio is large, it means that the matrix is close to be non-invertible or singular. So when this ratio is large, we get non-robust solution, which means that the solution is sensitive to errors. Here we see that it's sensitive to thermal noise. But it makes sense. It makes sense. The sensitivity to thermal noise comes from this inversion of a matrix which a high conditional number. So what did we do here? We added epsilon multiplied with identity matrix. What happens to this ratio? So instead of this ratio, we have eigenvalues. If you take symmetric matrix, you add epsilon I, the eigenvalues actually become plus epsilon. So this will be the maximum eigenvalue of the matrix gamma plus epsilon I, and this will be the minimum eigenvalue. So you see, epsilon plus max, it doesn't really matter, because if you add the small epsilon to the maximum eigenvalue, it's not going to affect it. But the denominator is going to be really affected. So you see, when epsilon is larger, this ratio becomes lower. So we decrease the condition number when we increase epsilon. So this is a really well-known method to make symmetric matrix more regular. That's why. So when you have this matrix is symmetric. Yes, all the eigenvalues are positive. If you have symmetric matrix, okay, so you have the maximum eigenvalue and the minimum eigenvalue, they are finite. And then if lambda mean is 0, it means the matrix is singular. So of course you cannot invert a singular matrix. But even if it's not 0, suppose that it's full rank, but this ratio is high, so it comes closer to be singular. So if you want to decrease this ratio, you can add epsilon to the diagonal, which means you add epsilon to the eigenvalues, and then you decrease this ratio. So by decreasing this value, this ratio, this condition number, it means that you make this matrix more regular. That's why epsilon is called regularization parameter because it makes the close to singular matrix, it makes it more regular, this parameter. Okay? So this is a well-known method to regularize symmetric matrix. Okay? And we see it very beautifully that we obtained it from the way we use the trade-off between directivity factor and white noise gain. Let's see an example. By the way, instead of epsilon like this, instead of a parameter like this, sometimes we can, we can do something instead of epsilon. So this is the super directive, of course, with epsilon that depends on f. We can do some regularization like this. So instead of gamma 0 pi plus epsilon I, we can take 1 minus alpha this plus alpha this, which is similar, but it enables us to use alpha between 0 and 1. Because here, epsilon is between 0 and infinite. So here we can use alpha between 0 and 1. And the relation between epsilon and alpha is like this. So it's just another way to do regularization or trade-off between two values that we want to optimize. And we obtain the white noise gain and the directivity factor using this regularization. So if we go to the example that we showed before with the maximum directivity factor, and we take regularization coefficient alpha, so you see here in this example the white noise gain that is achieved, the white noise gain as a function of frequency for different values, different number of sensors. So the blue one is with 2 sensors, then 4 sensors, the green. The red is with 6 sensors, and the light blue is with 8 sensors. So different values. So this is the white noise gain, and for different values of alpha. So alpha is between 0 and 1. So if it's very small, if it was 0, it means that we don't give any weight. Okay, so because 0, it means we don't give any weight to the white noise gain. So the white noise gain will go to minus, we saw, minus 100 dB, minus 80 dB, very low. But so here, in this example, alpha is 0.001. So you see, alpha is not 0, it's larger than 0. So it didn't go down too much, the white noise gain. If we increase alpha, so it means we give more weight to the white noise gain, so it increases. And if alpha equals to 1, it means that we only optimize the white noise gain. Directivity factor, we don't care. So when alpha equals to 1, we obtain the beamformer that maximizes the white noise gain, which is the delay in sum. Okay? So this is the delay in sum in this case. Alpha equals to 1. So you see, we know that the white noise gain is maximal. See, it's maximal. So of course, as we increase alpha, the white noise gain increases. So if you compare the blue line here compared to the blue line here, it's larger. And here it's larger, and here it's larger, for any frequency. And we can also plot the white noise gain as a function of alpha for different numbers of sensors. So you see here, number of sensors 2, 4, 6, 8. So for a given number of sensors, as we increase alpha, this is for 1 kilohertz, 2 kilohertz, 4 kilohertz, 8 kilohertz. So for a certain frequency, let's suppose that we work with 4 kilohertz. As we increase alpha, we give more weight to the white noise gain. So you see the white noise gain increases. And for any number of sensors, it increases as we increase alpha. What happens to the directivity factor when we increase alpha? What do you think? What happens to the directivity factor? When we increase alpha, the white noise gain increases. So what happens to the directivity factor? Decreases. We pay for that. This is the trade-off. So you see that here the directivity factor as a function of alpha decreases. The maximum directivity factor is obtained for alpha equals to 0. But then the white noise gain will be very, very low. So we increase alpha, we increase the white noise gain, but the directivity factor decreases. So suppose, let's go back for just a minute. If I go back to the white noise gain, okay? So this is the white noise gain as a function of alpha. And this is for 4 kilohertz, for example. So I can choose alpha. You see if it's low, it's here. Suppose that I want to choose alpha such that the white noise gain will be larger than 0 dB. 0 dB here. So I will choose this alpha. What is here? This value. I will choose it for 4 kilohertz. If I want it to be also larger than 0 dB for 1 kilohertz. So alpha for 1 kilohertz will be this value. So for each frequency, I can choose alpha, for each frequency, different alpha, such that the white noise gain will be larger than 0 dB. Or a different threshold. But suppose that the threshold is 0 dB. Okay? So alpha depends on the frequency, the optimal alpha. And then, if I go to the directivity factor, you see that the directivity factor for this alpha, it will be lower than the maximum that I can achieve because it goes down using this value. So I can compute the directivity factor for that alpha and for that frequency. It will be lower than the maximum directivity factor that can be achieved. Because there is a trade-off between white noise gain and directivity factor. Okay? Any questions? We call this method robust beamforming. So if we use robust beamforming for super directive beamformer, so it's robust super directive. If we use it other methods, so it can be robust based on what are the errors. Okay? It's very nice to mention also, this is something which is nice, because I talk here about thermal noise. Many times when you manufacture, when you design a beamformer, you assume that the sensor are in certain positions. But in practice, because of inaccuracies in the manufacturing process, sometimes the sensors are not exactly in the place where you designed it. Suppose that you have smart glasses and the microphones are not exactly where you designed. There are some errors. So this kind of error. So you want that your design will be robust to these errors. And there are other errors, important errors. Sometimes you think all the sensors are the same. So the sensors have sensitivity, which means magnitude sensitivity and phase sensitivity, which are the same. All the sensors are ideal. But when we manufacture sensors, microphones, antennas, underwater communication, any sensor, They are not ideal. They are not the same. So we have some differences between the sensors. And then we can ask ourselves, how is the performance sensitive to differences between the ideal sensors and actual sensitivity of the sensors and the differences it will affect? So when you look at the design or at the specification sheet of a sensor, you need to verify what is the error of the manufacturer regarding the magnitude response, phase response, frequency response, and so on. These are important specifications because it tells you what can be the errors or the differences between sensors. And then you can design your filters or your beamformer or whatever device in actual design that will be robust to these errors in practice. Okay? And this is important. This is robust design. Because if you just take the mathematical model, you assume everything is correct, you go to a real design, a real device, it doesn't work. And you don't understand why it doesn't work. Because you didn't verify what are the assumptions and what are the errors in the actual device. So you need to take these specifications into account when you design a device in practice. This is very important. Here we see the beam patterns that are achieved by the robust super-directive beamformer. So you see here, we see this is for 1 kilohertz, 2 kilohertz, 3 kilohertz, 8 kilohertz. When alpha is small, it means that we give less weight. It's small, it's larger than 0, but it's less weight to the white noise gain. We give more weight to the directivity factor. So we get these beam patterns. You see why all the main beam are directed to 0 degrees? Why? Because here the beamformer, what kind of beamformer? Super directive. And super directive that is designed with uniform linear array, we can prove that the max super directivity is obtained for theta d equals to 0. Very nice. It shows that you listen to what I say. You understand. Very good. Very good. It's important. So the main beam is directed to 0 degree. Very good. Now, we see that when the frequency increases from here to here, from here to here, so on, so this is high, 8 kilohertz compared to 1 kilohertz. You see the main beam becomes more narrow. Okay? Because we didn't put any constraint on the width of the main beam. So generally, if we don't put any constraint, it tries to maximize with the minimal constraints. So the minimal constraint is that the main beam is directed to 0 degrees. We didn't put any constraint on the width. If we had constraint, the performance will degrade in other, regarding other measure. Okay? But here we didn't put, so generally it becomes more narrow when we increase the frequency. Now, if we increase alpha, what will happen? What will happen to the beam pattern? If we increase, okay, let's think for a moment, okay, gradually, okay. So when we increase alpha, we give more weight to the white noise gain. What will happen to the directivity? Will come down, will decrease, okay. If the directivity factor decreases, what does it mean on the width of the main beam? If it decreases, the directivity factor decreases, so it becomes wider. Because if we have a wide main beam, So what is the directivity factor? It's actually the ratio between the value with this direction. With this direction is always 1, 0 dB. Okay, so it's always 1. And we divide by the integral over all directions. So if the main beam becomes wide, it means that we have lower directivity. Okay, so for each frequency, when we increase alpha, let's increase alpha, and we will see that the main beam becomes wider. Now you understand what is the relation between alpha and the width of the main beam. Oh, sorry, here. You see here now, alpha is 0.1 instead of 0.01. So we increase it by a factor of 10. And if we compare the main beam, it becomes wider. If we increase alpha, just a minute, if we further increase alpha to 1, it's even more wide. See, it becomes wider. Okay? So I will jump, so you can, here, 0.1, 1. I will jump between these two. Okay? You see? 0.1, 1. 0.1, 1. See what happens? The main beam becomes wider when I increase alpha. It makes sense. Any questions? The next topic will be null steering with fixed beamformers. Okay, so I prepare you. I will talk about it tomorrow. But I just want you, because I want to give you some discussion. What is null steering? You see, with fixed beamformers, I assume that I know directions. So I know the direction theta d, the direction of the desired. Now suppose that I have some interferences from certain directions. So I remind you that with fixed beamformers, I assume that the noise field is either spatially white or diffused or combination of these two. Combination of these two with the parameter epsilon or parameter alpha, what we showed. So combination, it means that I try to optimize both with a trade-off. So this is a trade-off parameter. So if I have an interference from a certain direction, I will not be able to reduce it. So with null steering, I try to add more constraints, additional constraints, that for certain directions, I will have zero of the beam pattern, zero response. Why? Because I know. Suppose that either I know or I can estimate or find the direction of interference. So I can modify the fixed beamformer. Okay? So sometimes I do it offline in advance and I fix it. Sometimes I do it online. Okay? Suppose that I design a smart glasses. So I can design that the response, the maximum response, will be towards this direction. And I can maybe put a null on another direction. What will be another direction? This is a nice question. Okay? Suppose that I take the smart glasses and I put the desired source, I will put it in front of me. This will be the direction. And I want to put a null on a different directions. Okay? So let's think. Smart glasses, they have microphones. They have also loudspeakers here. And I don't want to get feedback of the loudspeaker at the output of the beamformer. So I will add nulls on the loudspeakers, the signals that come. So the source will come from the direction of the loudspeakers. So I don't get feedback. Remember that sometimes when they increase the volume here, you hear like howling or very loud noise because of the feedback. This is very disturbing. So it's very disturbing for hearing aids. So if we want to add nulls to that feedback, to reduce that feedback, we add null on the beamformer. So we will talk about null steering. It's a very practical way, as long as we know the direction or we can estimate it. And if we don't know these directions accurately, theta d, we don't know accurately because we estimate it online. Or we estimate the direction of interference. We don't know them accurately. What do? We design robust beamformers that is robust to these errors. So it's called robust beamforming. When we talk about robust beamforming, you need to know it's robust regarding to what? So regarding to these directions. So you can read about robust MVDR, robust LCMV, robust beamformers. When the robust, either regarding the noise or regarding the directions, so you can modify this optimization regarding to some errors, okay? So we will continue to discuss the null steering, and then we'll continue with adaptive beamforming, which will not take us much time because it's very similar to signal enhancement. We just change, instead of steering vector that is based on the relative transfer function, it is based on the directions. Questions? Very good. Okay, so don't forget I gave you assignment, and if you have more time you can do more assignments, more problems, and it's important that you read the slides so you understand the material if you have questions. So tomorrow will be the last day, so please ask questions that things which are not clear. Let's make everything clear, okay? And we meet today because today there is a culture event, and we also have dinner together. So see you afternoon.